Yeah, so I'm Neil Fortner with the HDF group, and I'm going to talk about selection IO, as Seren mentioned, which is a new feature we're developing in the virtual file layer. So the virtual file layer, you may be familiar with this already. It's sort of, it sits between the library internals and the actual file system. So you have this sort of, uh, layer where the file driver will pass offset, length, and buffer to read or write from to the virtual file layer, and the file driver, which is the virtual file layer is just contains virtual file drivers. The file driver will translate that offset, length, and buffer into the actual call to the file system, which might just be a POSIX read or write call, or it could be something more complicated, for example, in the MPIO file driver. And so this is a pretty simple interface, and it maps pretty directly to traditional POSIX file systems. So here's an example of how that works. So these are the actual definitions of the callbacks for the file driver. We have read, and you see it gets an address, size, and a buffer. And then write, same thing, address, size, and buffer. And so if you have this, I'm going to be using this 5 by 10 or 10 by 5 array is an example here. If you're selecting the first 3 columns, then that gets translated to 5 different read calls. A read at 0, 3, length 3, a read at 10, and length 3, and so on. So that works fine for POSIX, where because to a POSIX read call, you can't batch multiple runs into that single call. But there are other cases where we might want to be able to pass more information to the underlying file system, or the file driver might be able to do something with more information on the shape of the entire IO request, not just a single block. So yeah, as it says, with the existing scheme, you must break non-contiguous IO into a series of IO calls, one for each block. So here's some examples of systems that could take advantage of knowing more of the knowing the shape of the entire IO request. So there's MPIO, where you can build up an MPI data type and pass that data type to MPI. And especially in the case of collective IO, the MPI can be a lot smarter about how it does things, and it might move data around in ways that make it more efficient. Also for asynchronous IO, if you have an asynchronous IO system underneath, like an async interface, you could, if the file driver knows about all the different blocks, it can fire off an async IO request for each of those blocks asynchronously in a loop, and then at the end it can wait on all of them, and that gives the file system more flexibility to do things in parallel where it can. Also for subfiling, which is a feature where we break the HDF5 file into multiple files that are stored on different targets. That gives the file driver more information about how to split up the IO requests and send it to the different targets. And also object stores may have an interface that allows for non-contiguous IO. If you're implementing an object store, it's a UFD. And there are other cases. There are other cases of file systems that where they can be accelerated by having more knowledge. I could look those up if anyone's interested. All right. So you might be wondering about MPIO, because we support collective read and writes with the MPIO file driver, and we do it is we build a complicated MPI data type. So the way it works right now is we sort of have this its own this sort of like backdoor channel built into that sort of runs in the undocumented property in the property list that gets passed to the file driver. And the library has code written specifically for the MPIO file driver, where the library builds up the MPI data type and passes it to the file driver. And it passes it in kind of a weird way. It passes it through, like I said, this undocumented backdoor channel, and the parameters it passes to the read or write call are somewhat, well, they don't really reflect the actual IO that's going on, because it's really this weird shaped thing. It's not, even though it passes an offset in length. And so, we, for pretty obvious reasons, we don't think that this pattern is great. It's code written specifically for one file driver, and we want the library's code to be generic to work with any file driver, and we want any file driver, even ones written by external developers, to be able to take advantage of having full knowledge of the shape of the IO. This talk is talking about ways that we're planning to enable that. So one way, this is sort of the simplest way. The first way you think of is we pass a vector of offset length and buffer triplets. So here, here's what the callbacks we have implemented right now in the branch. So yeah, you can see it passes a count, and then arrays of addresses, sizes, and buffers, and also memory types, but that's not as important. That tells you if it's metadata or raw data. And same thing for the write here. So when you take the same example that we looked at last time, whereas previously it was 5 read calls, now it's a single read call, just with arrays of length 5. And so that's, fundamentally the same, but it gives the file driver knowledge at the start of the entire IO request. So the file driver can, build an MPI data type or make read call, vectorized read call to the underlying file system, or fire off 5 asynchronous reads or what have you. And so that works pretty well, but it's not as efficient for example, for this case. Imagine that there are 1,000 rows, and there's going to be 1,000 elements, and the file driver is going to have to iterate over all of them. So because this is a simple repeating pattern here, we wanted to have a way to sort of communicate that pattern without having to go over every single block, right? So the way we were thinking is selection IO, where we pass an HDF5 dataspace that has a selection in it. And we pass one for the file and one for the memory, because the memory might have a different shaped buffer too. That's also the case with vector IO. You might have to break it up for blocks in memory instead of blocks on disk. And so that is, as you can imagine, it's much more efficient for repeating patterns. But the thing is, we don't have, and so it passes all that information very efficiently, but there isn't a very good public API for sort of retrieving that pattern information. I mean, there are in some cases, because you can get the blocks, but it's not as general as we would like. It's a HFS get hyper block list, I think. And so for some simple cases, you could just use that, and that would give you the pattern pretty quickly, like for this case, the example. But if it's a more complicated repeating pattern, that would be very difficult to use. So we have some ideas for a more generalized way to get the pattern, but we haven't implemented that. So, but that is on the list of things to do. So here's what the callbacks look like. So you can see it passes a count again, it passes an array of memory spaces. It might just be one space. In fact, most cases it will be. Then an array of file spaces, then an array of offsets and element sizes, which defines what the size of each element in the data space is. because we don't convert it straight to element of or array of bytes. We leave it as like disk space, data type elements, and then again, an array of buffers. So that, for the example we've been using, that translates to a read selection. We'll assume it's contiguous in memory. And then the file selection is hyperslab with a start of 0, 0 and a count of 5, 3. And so that just defines this block here. And you can imagine if there were 1,000 rows, then it wouldn't get any more complicated. It would just be 1,000, 3. So you can see how that's much more efficient for IO patterns. So here's where we're at right now. We've added the file driver callbacks. As you can see, we've added the public H5FD calls where you can sort of call these file driver routines directly. Although, in most cases, you won't use that from most applications because you don't want to go around the HDF5 library. And the library will build these selection IO requests and pass them down to the file driver layer in most cases. Right now, you have to enable it in our branch, but we're planning to eventually have this be the default way that things work. And the file driver code will check and see if the file driver actually implements vector or scalar IO, and it'll translate the selection calls to either vector or scalar, depending on what's supported by the file driver, if it doesn't support selection IO. And we've implemented vector IO support in the MPIO file driver, including with collective support, and we've verified that that works correctly with the library passing selections to the file driver layer, and then that gets translated to vector, and then everything works even in collective mode. And we've verified that there's no significant performance hit. In some cases, it's a little bit faster, in some cases, a little bit slower. So within margin of error from using this code, we haven't implemented cases where we would expect to see a speed up yet, because the only place that we've implemented that takes advantage of non-contiguous IO is the MPIO file driver, and that was already taking advantage of it previously just through this undocumented backdoor path. So what's remaining is we want to support the remaining use cases, for example, data type conversion or chunk cache in IO pipelines. And we want to, once we've got everything implemented and verified that there aren't any substantial downsides to the new code, we want to remove the old code, especially that parallel hack that I was telling you about. And then we want to implement support for selection IO in the MPIO file driver in addition to the existing vector IO implementation. And we want to implement those routines I was talking about for the more efficient traversal of selection patterns. And then also implement other VFDs that benefit from selection IO, including subfiling. And that's all I have. Any questions?
Right, we have a few minutes for questions.
There is one from Werner in chat room.
Yeah, I can't see the chat. Let me see if it's...
Oh.
Oh, it's in more maybe? No. Yeah, can you read it? Sorry.
Yeah, might it be possible to make use of the memory paging capability of a VFD such that a H5D read actually does not read at all, but just exposes a memory location where the file components are paged in and out? Obviously, that would only work for uncompressed, unfiltered data and probably require new public HDF5 APIs.
So you're talking about a VFD that basically has a cache built in? Am I understanding that right?
I think, Werner, just unmute yourself.
Yeah. Yes, I can try to talk as well. I mean, if you have a memory paging capabilities to just use that instead of reading data using POSIX functions.
Mhm.
It would be quite useful and probably more efficient than reading the data and then you just page it in and page it out automatically from your OS.
Right.
And if a VFD could provide that capability, it could tell HDF5 to kind of forward this paging capability. That's the idea. And like if you make a changes to the VFD API now, maybe such a feature could be built in as well.
Right. Well, so we have a page buffer, which is conceptually a similar thing in HDF5. Although I should mention that that's one of the things we don't support in selection.io yet. But that tries to, at least for metadata, it will read in, fixed size pages and hold them in a cache in HDF5. Although I think it only holds one page at a time. I may be wrong on that. But in principle, I don't see any reason that wouldn't work with the existing interface with the VFD, because as long as the VFD knows the the layout of the file, then it can get the information from a page, the cache page, or from the POSIX file, as long as it maintains consistency, right?
I mean, the current problem with H5D read is that you already have to provide a pointer, a memory location, and then HDF5 library is copying the data there. But I'm thinking about a way to even avoid the copying the data.
The library shouldn't be copying the data there. It's the VFD, right?
The H5D read, for instance, you have to provide a memory location, and then it will be filled with the data which is somehow retrieved from a file.
Right. Well,
so we would need rather a function which gives you a pointer to the data rather than copying the data to memory which you already provide.
Are you talking about HDF read or the file driver?
Well, effectively in HDF read, you would need to have a different way to get the data instead of copying there, but the file driver of course needs to support it.
Well, yeah, so I think you could implement a file driver right now that could do what you're saying. I don't know. Yeah.
But HDF read still would need to copy the data, even if it's paged internally by the file driver.
Well, it's up to the file driver to. Or you're saying you want to avoid a mem copy?
Yes.
We try to avoid mem copies in general. I think in the simplest case, I'm pretty sure that the file driver will get the actual user's buffer.
Yeah, but still the user has to provide a buffer. But if you page memory, you don't even have a buffer because it's already provided by the paging.
Oh, you're saying you want to just retrieve the buffer location from the file driver or something?
Yeah, something like that. Something
like a memory map?
Yes, exactly.
Mm-hmm. Yeah, it's an interesting idea.
Then if the application has a pointer to this memory map, it modifies the data. It doesn't even need an explicit write operation. It will be just paged through.
Mm-hmm.
Werner, maybe you can send us a little bit elaborate and send, and we'll definitely discuss it.
Yeah, that's good.
Okay. I can open a thread in the forum if you like, so we can discuss it.
Right.
Okay, I will do that.
Thank you.
All right. Thank you, Neil. And